This is Chapter 2, Lecture 1, Investigating Geologic Questions. We delved into observations and interpretations in Chapter 1. We'll go even further with that, with landscapes and rocks with this chapter. We'll introduce relative dating of Earth materials, landscape evolution, and look more at different types of geologic figures. We'll look at different types of data, investigate data versus interpretations, hypotheses, and we will use that information to see how we can solve geologic problems. This is the Mediterranean Sea. We want to know how it connects or doesn't connect with other bodies of water. I'll point out the Strait of Gibraltar. This is where we connect the Mediterranean with the Atlantic Ocean. It's just a thin strip of land separating the Mediterranean from the Black Sea on the other side. Okay. It's separating, of course. There's not a connection here, but there is a connection right here at the Strait of Gibraltar. At one point, this area was closed. There was not interaction with the Mediterranean. Didn't receive enough water to supply itself, and it dried up. We have salt deposits and then sand deposits showing that in the geologic record. There's also the Suez Canal. There was no link here before this canal was dug. But the reason why the Mediterranean Sea continues to exist the way we see it now is because it receives water from the Atlantic Ocean. Precipitation isn't enough to supply it with water. So without that, it would dry up over time. And it has in the past. Look at this exposure of rock. We have rounded sediment and let's see, a little bit less, well, you have finer sediments and then larger sediments. So it's not what we'd call well sorted because there's a variety in sediment types and sizes. We can compare this to deposits from the two environments below. The sediment here contains angular pieces. The sediment on the right contains rounded pieces. These probably formed in similar environments. Characteristics of older sedimentary rocks can be compared to modern environments to infer the environment in which the rock formed. Since this is so angular, let's say we probably got this from a steep mountain front. This is eroded more over time as a river with pebbles. So I'd say this is probably from a river environment as well, not knowing anything else about it. We can interpret the evolution or change of landscapes over time. These are 3 different models which show progressive change. The rock outcrop gets progressively lower and smaller in each model. From a mesa to a butte to a series of knobs. Right? And that's a landscape photo depicting that same thing, or just showing that same thing. Erosion creates these cutouts into the layers. Further erosion removes more rock, forming a butte. Once that resistant top layer is removed, we have these rounded hills. All right, so we can determine sequences of past events by looking at the positions of rock layers. In a sequence of layers, the bottom layers are deposited first, and the layers on top are deposited later. So lower layers first, upper layers later. That's a geologic principle, a guiding principle, that the youngest layer is found on top, unless something happened to tilt it or turn it over again. And the oldest rock is on the bottom. Another principle, cross-cutting relations. A fault can cut across or cross-cut rock layers. And since it cut those layers, it is a feature that's younger than those rock layers. Younger features can cross-cut older rocks or features. Another principle deals with pieces of older rocks. So these are rock clasts. These pieces of gray rock had to be weathered into pieces on the surface to be incorporated into the overlying tan unit. This older unit is exposed on the Earth's surface at some point and weathered, right? And then pieces of that older rock become incorporated into a younger unit. And the principle here is that a younger unit can contain pieces of an older rock unit. Another principle deals with the effects of molten rock or magma contacting another rock. So in this case, a magma invaded the rock sequence and solidified into the brownish gray rock. The magma caused effects along the contact by heating, baking the rock near the magma. So the principle is that a younger magma can bake older rocks and change them. And this is what helps us put everything in order from observations to interpretations in a rock sequence. And we'll look at this photograph and the different features that we see. The lower unit is gray and it displays these tilted layers. The middle sandy unit is on top of the tilted rocks. There's an upper coarse unit. It contains pieces of the lower unit, actually. Same material. There's no evidence of baking like from the last slide. We can conclude that the lowest unit is the oldest. It was tilted at some point and eroded. Became a source for these pieces up here. It was partly covered by the middle unit and provided those clasts for the upper unit. Look at this terrain in northern Arizona. So this dark gray black feature that I'm outlining is a lava flow emanating from the SP crater, which is a small volcano. These adjacent hills are also small volcanoes. The type is a scoria cone, and we'll go into that with our volcano chapters in the future. They've been eroded to various degrees. These light-colored areas are sedimentary rock, not volcanic rock. They're cut by several linear features that we can see and folded as well along the northern edge. So to summarize the features that we pointed out, you can look a little closer. This is an aerial view of the SP crater showing that lava flow. Looking at the same area, we can see it in terms of different types of maps. This is a shaded relief map. It shows the shape of the land by simulating light and shadows on the hills and valleys. Shows differences in elevation. A topographic map has elevation contours. There's a few rules for these. These lines represent lines of equal elevation. So everything on this line is the same elevation. And there's what's called a contour interval for any given topographic map. So the changes in elevation between each contour line is going to be the same. Perhaps it's 10 feet contour interval or 40 feet contour interval. It can show us differences in elevation very quickly, with the highest elevation points being these volcanoes in the SP crater. You can also look at the same area with a satellite image. It uses different wavelengths to show the distribution of different types of plants, rocks, and other features. Or you can look at this as a geologic map that's actually draped over a relief map, which shows the differences in distribution of rock units. We have this as the legend, gray being the lava flow, scoria cones, cinders and older flows, and then limestone being the sedimentary rock in the north, and then the faults are marked with these black lines. For what a geologist does, this could be the most informative, but they're all important and they're all useful. Okay, so we talked about the topographic map, topography being differences in elevation. This is a cross section that you're looking at, but it's also part of a block diagram, so we can see the surface. We're looking at different ways we could show differences in topography or elevation from one place to another. Elevation can be described in terms of meters, kilometers, or feet. It's the height above sea level. Relief is the elevation difference between two places. So if you're interested in hiking through a certain place and the relief is very high, it means you're going to have to work really hard because there's a huge difference in elevation that you're trying to cover. Steepness of slope, that's showing basically cliffs that drop sharply are of course described as steep slopes, whereas less steep areas are referred to as gentle slopes. We use cross sections and block diagrams to depict features in the subsurface. A block diagram is a 3D depiction. A geologic cross section, it's only a slice through the subsurface without showing the surface of an area. And then a stratigraphic section, it's a sort of idealized summary of geologic layers. That's what this is. So block diagram, cross section, stratigraphic section. We can look at this and infer the sequence of events that formed this specific area. And we'll use these block diagrams to do that very thing. So there's 3 stages in the formation of this same area as the previous slide. The first stage is a shallow sea covered in area. You see the blue water at the top. The second stage, we have sand deposits that came along the beach, and we see those on top. The water sort of receded. The third stage has erosion. It carved through that sand deposit and down into this limestone deposit as well. These are diagrams that you might see in terms of maps, cross sections, or block diagrams, just to show how an area might have changed over time. Now we'll get into qualitative versus quantitative data. We can first make some observations about this photograph. Those are descriptions conveyed with words or sketches. So I see gray colored rocks. In the background, I'm not sure, but these look a little darker than what's in the foreground. I see some sediment coming down off the rock. I see steam, some kind of gas, vapor coming off the rock as well. But quantitative data would be numeric measurements conveyed with numbers. So in a similar landscape, you could have a geologist noting the temperature of rocks from a thermal instrument was 200 degrees Celsius. We'll get into density versus weight. We had these wood block diagrams from the previous chapter. So what can you infer about differences between 3 blocks immersed in water? Each block has a different density. where density is equal to mass divided by volume. If you're less dense, you have less mass per volume, so you're going to float. If you're more dense, you have more mass per volume, you're going to sink. Weight is the downward force an object exerts under gravity. And with that, a person will have the same mass on the moon and on Earth, but the weights are different because gravity is different. Let's get into the geologic time scale. Now there's 4 main parts of the geologic time scale, which is based on the appearance and disappearance of fossils overall. The Precambrian, we start at the very beginning. 4,500 MA means 4,500 million years ago, or 4.5 billion years ago. That was before we had living things with shells and hard parts. After which we had the appearance of fish, plants, insects, and reptiles within the Paleozoic, 541 million years ago. This is a huge overview because there's a lot that happened throughout Earth history. Then into the Mesozoic, we see the appearance of dinosaurs and the first flowering plants. And then most recent being the Cenozoic, we have lots of mammals that showed up there too. Can take a moment to review Precambrian, Paleozoic, Mesozoic, and Cenozoic. Okay. This is kind of crazy, but let's look at a calendar, a year calendar, right? So January to December. To put the Precambrian in perspective for you, if Earth history were defined in terms of one calendar year, the Precambrian would have lasted from January all the way to mid-November. It's a huge amount of geologic time, where things on Earth were pretty simple. Not my favorite time on Earth, but it's kind of neat. And then the Paleozoic, when, in my opinion, things started to get really interesting, that only lasted till mid-December. And 2 weeks within mid-December would have been the Mesozoic. And then the last week would be the Cenozoic, where we are now. So life on Earth, relatively recent compared to entire planetary history and the rocks that were there in the Precambrian. And we talked about Precambrian, Paleozoic, Mesozoic, Cenozoic. There's further subdivisions that are subject to change with new information, but these are 4 main divisions. Those are eras. And then periods within that. Often these age periods are named from the place where they were first recognized. This time scale is not, as they say, set in stone. We recently changed these names. We've got the Paleogene, Neogene, and Quaternary, whereas before the Paleogene and Neogene were just tertiary. So it changes over time with new information. And we'll stop there for today.